As an application of the spin 1/2 part angular momentum addition that we just considered, there's a physical effect called the hyperfine splitting. And we'll consider the hyperfine splitting as it refers to the splitting of some energy levels in the ground state of the hydrogen atom. Now, the ground state of the hydrogen atom has some degeneracy, and the degeneracy is due to the fact that this electron can be with spin up or spin down. Therefore, the ground state, the spherically symmetric state, with principal quantum number n equals 1, L equals 0, and of course m equals 0 as well, is double-fold degenerate because of the spin of the electron. If you think also that, in fact, there's a spin of the neutron, the proton, I'm sorry, that is in the nucleus of the hydrogen atom, that adds two more possible states for the proton and two states for the electron, so it's two spin 1/2 particles. Now, in principle, you might think that, well, there's no need to talk about either spin too much. We can note that the electron states are degenerate, and that will be useful as we build the orbitals to understand the structure of atoms. But the fact that the proton has also a spin may not be relevant unless there's an interaction between those two spins, and precisely the hyperfine splitting of the ground state occurs because there is indeed an interaction between those two spins. As far as the electron is concerned, as it's orbiting the proton, or the center of mass of the orbit, the magnetic dipole associated with the proton will create a magnetic field, and it will be picked up, however small it is, by the magnetic moment of the electron. So this is an interaction between two magnetic moments. Since we focus on the electron Hamiltonian, we can consider this as the case in which the electron Hamiltonian, the electron magnetic moment, is moving in a space in which there's a magnetic field, that one created by the dipole at the nucleus. So let's consider, therefore, this situation. It will be the so-called hyperfine splitting, of the hydrogen ground state. So this will be an application of the spin 1/2 addition, and as well it will introduce some of the physical complications that you have to deal with when you try to do a practical computation. So in a sense, our spin 1/2 addition computation will be the key part of the computation, but we will have to deal with a few subtleties as we move along and try to do this. So I will begin by denoting what are the quantities we have in mind. So we have a proton and an electron, proton and electron. The proton has a magnetic dipole that will denote it as mu proton. And in general, it's given, it's proportional to the spin of the proton. And the constant of proportionality, we've discussed it a few times, Gp E over 2m of the proton times the angular momentum, spin angular momentum of the proton. For the electron, mu electron minus E over m electron, spin of the electron. This Gp factor, in the case of the electron, was a G equal of 2, and that canceled the 2 that is canonical in this formula. This Gp represents the quantity that multiplies the naive classical intuition of the magnetic dipole originating from the rotation of a charged particle into the real value. And for the case of a proton, of course, the proton is a composite particle. And therefore, you could expect that this GP could be unusual, and indeed it is, and the GP is a constant that is about 559. Particles that are not elementary have funny magnetic dipole moments. In particular, the neutron that would be neutral, you would say it should have no magnetic dipole moment, but the charge is not distributed totally symmetrically in the neutron between the three quarks. So at the end of the day, it does have even a magnetic moment. So these are our magnetic moments. And now what we have to consider is the Hamiltonian, the new piece in the Hamiltonian. So this is the Hamiltonian for the hydrogen atom, or in particular for the electron, interacting with a reduced mass nucleus. The extra Hamiltonian would be minus mu of the electron, dot product the magnetic field due to the proton, not at the proton, but due to the proton. So is the magnetic field at the electron due to the proton. Now this, since we have the magnetic dipole, over here we have E over ME, SE dot B of the proton. So this is the equality we're going to have to consider. The next step is trying to understand the magnetic field due to the proton dipole. So what is the magnetic field due to a dipole? Well, it's even very similar to the electric field due to the dipole. We have a little dipole, and the magnetic field will go in circles like that, and will fall off like 1 over r cubed. So the usual magnetic field due to the dipole at some point r will have a fall off like 1 over r cubed and some terms. But funnily, that's not the complete story, and that's sometimes noted in courses on electromagnetism, in particular a course you may take after your freshman year, and in which there is the need to add to this magnetic field a delta function at the origin. It is as if this full expression is just valid for r different from 0, but at r equals 0, this is an incorrect field configuration. This extra delta function can be understood intuitively by producing this dipole by a little sphere of charge that is rotating. You calculate the magnetic field outside, and the limit as the radius goes to 0. The magnetic field outside looks like this term here that I didn't quite write, but you can find in any book. On the other hand, as you take the ball going to 0, to produce that magnetic field, you will have to take a limit carefully in such a way that the end result is that the magnetic field, if you integrate the magnetic field on that little ball, that integral doesn't go to 0. And therefore, there's a residual magnetic field that is proportional to a delta function at the origin. And its value can be calculated by this limiting procedure or other methods. And the result is that this term takes the form 2 mu 0 over 3 times mu proton. There's two mu's here, the mu for magnetic moment and the mu for permeability of the vacuum. This is in SI units, you may prefer, in fact, I probably would prefer, if it was up to me, to use Gaussian units, but this is probably more easily found in books. So, so that's it. There's a contribution to the magnetic moment at the origin, which is an extra thing. Now, you would say, if I have this Hamiltonian, I have to evaluate this with all this magnetic field. And what am I supposed really to do? Now, we talked about perturbation theory and the Feynman-Hellman theorem. And the fact is that you are supposed to evaluate this operator that represents the extra term in the Hamiltonian inside the states, take the expectation value on states that you want to see how their energy shifts. And in general, if you have just one state to worry about, no degeneracy, you just compute the expectation value of the perturbation on that state, and that is the shift of energy. This is a slightly more delicate thing because we have 4 degenerate states. Those are the states with the spins of the electron up and down and spins of the proton up and down. So you have 2 and 2, so 4 basis states. They're all degenerate before you put this Hamiltonian. And the rule, in order not to get the wrong answer, is that for those states, you still can't quite evaluate the expectation value, but if you find the states that diagonalize the total Hamiltonian, you can pick any of those states and compute the expectation value of this delta H in it, and that will be the shift of energy of the state. So the formula is still valid, but you have to only use it for those states that are already diagonal. So what are the states that you will have to consider? Well, these are 4 states in which the spatial part of the wave function will be the psi 1, 0, 0, is the electron with n equals 1, L equals 0, and 0. And it will be tensored with either of 4 states. I'll write them like this. An up, up, an up, down, a down, up, and a down, down, where these refer to the spins of the proton and the electron. So there are 4 states that have to be evaluated, have to be reorganized into eigenstates of this Hamiltonian. They all share, however, the same spatial wave function. So I could evaluate the expectation value on the spatial part first, and then worry about the spin part. So this is what we're going to do. We're going to think of this Hamiltonian, extra piece in the Hamiltonian, evaluate it for these states, but we really, in order to find the perturbations of the energy, we have to use states that diagonalize this, and the problem is going to be in the spin part, because the wave function, the spatial wave function, is always the same. So what happens when you try to do this calculation? Well, in principle, you're supposed to put this BP in here and evaluate this quantity for this states. And we're doing only the spatial part first. So as we do the spatial part, here is what happens. This whole term that I didn't write completely vanishes for any state that has L equals 0, in fact. It can't be shown. I will not do the computation here because that's not relevant to the example, not directly relevant. If you want to check this, maybe we'll discuss it as well in other in an addendum or in some other video. But if you have here that this term doesn't contribute, by the time you insert the spatial wave function, only this term will contribute. Let's see what happens to delta H. Delta H effectively will be, look at all this thing, E over ME, SE, but BP will have this 2 mu 0 over 3 mu p, and mu p is gp e over 2 mp sp, so you get se dot sp. So I just substituted here and ignore this term, and you would have the delta of x. So this is the only part that is going to contribute. The 2's cancel, and I can clean up this a little bit. E squared, or gp mu 0 E squared over 3 me mp se sp delta of x. So, now, indeed, let's put this wave function into play. So the relevant part of delta H, now apply the spatial part of the wave function from both sides to this thing. And we'll still call the result delta H. Maybe it should be called a little different because we're doing something to it. But let's just call it delta H. At this moment will be gp mu 0 E squared over 3 me mp. And the wave function comes with psi and psi. 2 psi's, a psi star psi, but it's integrated over space. Nothing else has spatial dependence. The wave function, the spin operators live in another world, not in the x space. And therefore here the only thing you get is psi 1, 0, 0 at 0 squared. And this is still an operator. We have SE dot SP. So this is just a spin operator. We've taken care of this part. We can simplify it a little more. If you recall the wave function for the ground state of hydrogen, its normalization. It involves the square root of pi times the square root of the Bohr radius cubed. So at this moment, the full result here is gp mu 0 E squared over 3 pi me mp 1 over a0 cubed, the pi and the 1 over a0 cubed, se dot sp. Okay, so we have our operators ready. So what comes next? We have to understand this part, the product of spins.